Hello everyone, my name is Isan. In this video I'm going to investigate the introduction to fundamentals of deep learning from a high-level perspective. Alright, an important question in any machine learning problem is, with all the different algorithms in machine learning, how we can choose the best. The answer requires principal information about the purpose of the work. So if we want to predict or forecast the target values, then we should use supervised learning techniques such as neural network and Bayesian method that we know the correct answer previously, or in other words, we have a labeled data. So in case of supervised learning, if we want to predict the out of continuous values, meaning that we are trying to map input variables to some continuous functions such as forecasting the probability of a day being rainy, the regression would be an appropriate option. On the other hand, if we are instead trying to predict results into discrete outputs, or we need to map input variables into discrete categories, for instance, predicting that if somebody has cancer or not, we might use supervised classification. However, if we are not trying to predict a target value, or we don't have any labeled data, then we need to look into unsupervised learning. In this case, if we want to fit our data into some discrete groups, we might need to look into clustering. And finally, if we need to have some numerical estimate of how strong the fit is into each group, we probably should look into density estimation algorithms. Okay, while machine learning is often described as a subdiscipline of artificial intelligence, it's better to think of it as a current state of art. It's the field of artificial intelligence which today is showing the most promise at providing tools that industry and society can use to drive change. In turn, it's probably most helpful to think of deep learning as the cutting edge of the cutting edge. Actually, machine learning takes some of the core ideas of artificial intelligence and focuses them on solving real-world problems with neural networks designed to mimic our own decision making. Deep learning focuses even more narrowly on a subset of machine learning tools and approaches, and also applies them to solving just about any problem which requires human or artificial thought. This definition might be confusing, so let's start with an example. Let's take a look at this picture. How we recognize a square from the other shapes. The first thing our eyes do is check whether there are four lines associated with this picture or not. That indicates a simple concept. If we find four lines, we further check if they are connected, close, perpendicular, and that they are equal as well, and that represent the nested hierarchy of concepts. So we took a complex task, which is identifying a square, and broke it in simple, less abstract tasks. So deep learning essentially does this at a large scale. The human brain first learns simpler concepts and then combine them represent more abstract ideas. Motivated by these learning techniques, researchers have devoted a lot of efforts for using many levels of abstraction and processing to solve computational problems. In the literature, deep learning has also been referred to as deeply structured learning, hierarchical learning, deep feature learning, and deep representation learning. One of the most common and popular deep learning structure is the multi-layered models of inputs, commonly known as deep neural networks, which comprise multiple levels of nonlinear operations. There might be fundamental question that what is exactly the difference between machine learning and deep learning, and also why deep learning nowadays. The most important difference between deep learning and traditional machine learning is its performance as the scale of data increases. When the data is small, deep learning algorithms don't perform that much well. This is because deep learning algorithms need large amount of data to understand it perfectly. Moreover, deep learning algorithms heavily depends on high-end machines, contrary to traditional machine learning algorithms. This is because the requirements of deep learning algorithm include GPUs, which are an integral part of its working. Deep learning algorithms inherently do a large amount of matrix multiplication operations. These operations can be efficiently optimized using a GPU because GPU is actually built for these purposes. On the other hand, in machine learning, most of the applied features need to be identified by an expert and then hand-coded as per the domain and data type. For example, features can be pixel values, shapes, textures, positions, and orientation. The performance of most of the machine learning algorithms depends on how accurately the features are identified and extracted. Deep learning algorithms try to learn high-level features from data. This is a very distinctive part of deep learning and a major step ahead of traditional machine learning. Therefore, deep learning reduces the task of developing new features extracted for every problems. Like convolutional neural network will try to learn low-level features such as edges and lines in early layers, then part of faces of people, and then high-level representation of face. Usually, deep learning algorithms takes a long time to train. This is because there are so many parameters in a deep learning algorithms that training them takes longer than usual. State of art, state of the art of deep learning algorithm ResNet takes about 2 weeks to train completely from scratch. It's a lot. Whereas machine learning comparatively takes much less time to train, ranging from a few seconds to few hours. This turn is completely reversed on testing time. So at test time, deep learning algorithm takes much less time to run. Whereas if you compare it with k-nearest neighbors, one of the machine learning algorithms, test time increases on increasing the size of data. Although this is not applicable on all machine learning algorithms, as some of them have small testing time too. Here we can see some of the application of deep learning, like object recognition, speech recognition and signal processing, natural language processing, robotics, automated vehicles, AI games, and etc., which today is widely used. Okay, here we briefly define the three main classes of deep learning architectures, namely generative, discriminative, and hybrid deep architectures. Generative deep architectures, which are intended to characterize the high-order correlation properties of the observed or visible data for pattern analysis or synthesis purposes, and characterize the joint statistical distributions of the visible data and their associated classes. In the latter case, the use of Bayes' rule can turn this architecture into another architecture, which is discriminative one. The discriminative deep architectures, which are intended to directly provide discriminative power for pattern classification, often by characterizing the posterior distributions of classes conditioned on the visible data. Hybrid deep architectures also where the goal is discrimination, but is assisted with the outcomes of generative architecture via better optimization and regularization, or when discriminative criteria are used to learn the parameters of any of the deep generative models in generative architectures. Alright, in the few following slides, I'm going to briefly overview the relevant deep learning models such as convolutional neural networks, deep reinforcement learning, stacked autoencoder, and DBMS. The convolutional neural network is a discriminative deep architecture. At the first glance, a CNN may appear to be quite similar to an ordinary artificial neural network, since both architecture consists of neurons having learnable weight and biases. As you might know, traditional feed-forward artificial neural networks receives an input like a single vector and transform it through one or more than one hidden layers. Each hidden layer comprises a set of learning units called neurons. The neurons of a hidden layer are connected in a fully meshed fashion with those of the previous layer. The last fully connected layer is referred to as the output layer. Each neuron receiving several inputs takes a weighted sum of them, passes it through an activation function, and responds with an output. In contrast with the traditional feed-forward neural networks, the deep artificial neural network structure is a convolutional training method in many areas, but with full connectivity between nodes suffers from the burden of dimensionality. When the inputs becomes too large and complex, such as the training of high-resolution images, the convolutional artificial neural network cannot process well. Actually, it cannot perform well. Therefore, the convolutional layers were proposed instead of full connectivity and the neural network layers. The architecture of a deep CNN or convolutional neural networks deals with the multi-channeled image as the input. To deal with this complex input, the CNN consists of several layers of convolutions with nonlinear activation functions to compute the output. Thus, the CNN comprises localized connections whereby each region of the input is connected to a neuron and the output. So each layer applies different filters and combines their results. In addition, the CNN consists of pooling layers for subsampling. During the training phase, the CNN automatically learns the values of its filtered biases on the given task. For example, for classifying images, as you can see in the figure, assume that raw pixel cat image as shown here are the input of CNN. In its first layer, the CNN may learn to detect the edges from the raw pixels. Then, in the second layer, the CNN employs the edges to detect simple shapes. In this fashion, the subsequent layers, by using these shapes, the CNN may be able to learn higher level features like facial shapes and so forth. And the final layer, a classifier is used to exploit these high-level features. Deep CNNs have proved to be quite successful in learning task-specific, features, which have provided much improved results, particularly on different computer vision tasks. In contrast with contemporary machine learning techniques. Generally, the CNNs are trained by employing supervised learning method, whereby a large number of inputs and output pairs are essential. However, obtaining a substantially large training set has been a key challenge in applying CNNs. The next model is recurrent neural network. The idea behind RNNs is to make use of sequential information. In a traditional neural network, we assume that all inputs and outputs are independent of each other. But for many tasks, this is very bad for many tasks. So if you want to predict the next word in a sentence, you better know which words came before it. RNNs are called recurrent because they perform the same task for every element of a sequence, with the output being dependent on the previous computations. Another way to think about RNN is that they have a memory which captures information about what has been calculated so far. So in theory, RNNs can make use of information, arbitrarily long sequences. But in practice, they are limited to looking back only a few steps. The depth of the RNN may be as large as the length of the input data sequences. Therefore, the RNN is particularly useful for modeling the sequence data in text and speech. Neo-optimization methods to train generative RNNs that modify stochastic gradient descent have appeared in the recent studies, if you look at this. Okay, another model which I'm going to introduce is stacked autoencoder. The autoencoder architecture briefly attempts to construct a high-dimensional input into a low-dimensional embedding, and then uses that low-dimensional embedding to reconstruct the input. An autoencoder refers to an artificial neural network aimed to learn efficient coding by encoding a set of data. If the autoencoder architecture consists of just linear neurons or just a single sigmoid hidden layer, the optimal solution obtained by the autoencoder is correlated to the principal component analysis, or PCA. Then the feature which is learned by the autoencoder is used to train another layer of autoencoder, and so forth. The learned weight via this process are eventually used to initialize a deep neural network. The next architecture worth mentioning is the deep Boltzmann machines, or the DBMs. Although you will need to briefly review the shallow Boltzmann and restricted Boltzmann machines in literatures. A Boltzmann machine is a network of binary stochastic units with an energy defined for the network. While learning is inefficient in a shallow BMs, or Boltzmann machines, it can be made quite efficient in an architecture called the restricted Boltzmann machines, or RBM, which does not permit the connections among units on the same layers. Restricted Boltzmann machine is an algorithm useful for dimensionality reduction, classification, regression, collaborative filtering, feature learning, and topic modeling. After training one RBM, the activities of its hidden units can be considered as data for training a higher level RBM. This method of stacking RBMs permits training many layers of hidden units in an efficient manner, and this consists in one of the most common deep learning strategies. As each new layer is added to overall generative model of the RBM improves significantly. In addition, RBMs offer a popular architecture to carry out the pre-training. For instance, in some cases, researchers considered a stack of RBMs whereby the learned features activations of a single RBM are served as the input data for training the following layer of RBM. Once the pre-training is completed, the RBMs are unfolded to construct a deep network that is fine-tuned by employing the backpropagation algorithms. The RBM stack is also referred to as the deep Boltzmann machines, or deep belief networks, DBNs. The pre-trained DBMs can be used to initialize a deep neural network and train with a backpropagation similar to that in the stacked autoencoder. And last but not least, deep reinforcement learning is also another broad model of deep learning which is widely used in different research domains nowadays. Deep reinforcement learning combines the strength of both supervised and unsupervised learning methods. In a reinforcement learning method, sparse and time delay labels are used based on which the agent has to learn how to behave in a given environment. In other words, reinforcement learning enables an agent to learn by interacting with its environment. In this manner, the agent continues to build upon its experience so as to maximize its long-term rewards. The most well-known reinforcement learning technique is Q-learning, a simplified architecture, recently showing in this figure, which you can see as it has three different neurons, network, and state. Also, this deep Q network is patented by Google, have emerged to represent the Q function of the Q learning with deep neural network architecture. Many improvements to the deep Q networks have recently been proposed that include double Q learning, prioritized experience reply, dueling network architecture, the extension to continuous action space, and so forth. And thank you everybody. Here is the resource references that I've been used to prepare these slides.